Hello everyone, welcome back to the lecture of parameters of MoS transistor. Here we are going to see parameters like transconductance, output conductance, threshold voltage and figure of merit. The objective of this lecture is we are going to understand the different parameters of MoS transistor. After learning of this, you will be able to define the parameters and their significance of the MoS transistor. The contents we are going to see are the parameters of threshold voltage VTH, transconductance GM, output conductance GDS and figure of merit omega naught. We have seen in the previous lectures operation of the transistor, then current derivations in the MoS transistor. The operation which we have seen already, one is the cutoff region with no current, saturation, non-saturation region with current and with channel formation, and saturation region with the pinching of the channel and current flowing, maximum current in the saturation region and current is varying in the non-saturation region where current is equal to 0 in the cutoff region. All these we have seen in the previous lecture. Then as per those operations, we have derived the current equations. The current in the cutoff is 0 and it is in the non-saturation and it is in the saturation region. All these we have seen in the previous lectures. Now let us see other parameters of VTH, transconductance, output conductance and figure of merit. First starts with threshold voltage. It is representing as VTH or VT. Some textbooks are following as VTH or some textbooks are following VT, and for NMOS transistor they are following as VTN. For the PMOS transistor they are following as VTP. For the depletion mode transistors they are representing as VTD, threshold voltage of the depletion mode transistor. So in different representations they are representing, but definition is same for all the threshold voltages. Threshold voltages of NMOS transistor or PMOS transistor or depletion transistor with representation of all these is same. That is, let us see what it is, what is the representation of that and what is the equation form of the VT. Actually, this VT is required, minimum voltage it is actually. So, VT is the minimum gate voltage below which the current is equal to 0. That means, below the gate voltage of below the threshold voltage, the current is equal to 0. It means there is no conduction. That we can define in another words, another terms. We have enhancement transistor and depletion transistor both. Enhancement transistor means no channel physically. Depletion transistor means a channel physically. Therefore, depletion transistor is defined in another terms. Initially it is on and initially off transistor is enhancement transistor. So, initially off transistor is enhancement transistor and on transistor is depletion transistor. To make enhancement transistor from off to on, some voltage is required, that is called VT. And to make depletion transistor from on to off, some voltage is required, that is called minimum VT. So, switching an enhancement mode MoS transistor from off to on state, this VT is used. Similarly, switching a depletion mode transistor from on to the off state, it is required. Overall, below this threshold voltage, the transistor is not having any conduction. So, that is VT is the minimum gate voltage which can be applied at both enhancement and depletion transistors for the conduction. The mathematical equation for this can be modeled as VT is equal to phi ms into QB minus QSS by C0 plus 2 phi Fn, where QB is the charge or unit area in the depletion layer beneath the oxide. QSS, this is the QSS, is charge density at SiO2 interface, that is at the channel part, and C0 is the capacitance per unit gate area, and phi ms, this is equal to, this is the phi ms, this is work function difference between gate and silicon, and phi fn, this is equal to Fermi level potential between the inverted surface and the bulk silicon. All these are defining the material properties. Since VTH voltage or VT voltage, that is threshold voltage, is the voltage defined at gate to make a channel here. So channel means just it is simply physical property. We are changing the charge from positive to negative or negative to positive under the gate region. So therefore it defines the material properties of this SiO2 interface, the charge of substrate, and the materials which are used for the gate and other doping concentrations also. So all these are defining the material properties. Therefore all these values are fixed once the transistor is defined and designed. Therefore Vt is always fixed. It is constant value once the transistor is fabricated. And let us see the definitions of QB, which we have seen here, QB, QSS and C0 values. So QB is equal to, this is the formula, that is a charge, and phi Fn, QSS. Here again the variable is nothing but all these are constants, where K is a Boltzmann constant, temperature, charge and etc. So here the variable is VSB, substrate bias potential. So here all these are the representations. Substrate bias potential is representing as VSB, Q is the electron charge, and impurity concentration is defined with Ni, and epsilon Si is permittivity of silicon, and Ni is this one. Ni is intrinsic electron concentration and K is the Boltzmann constant. So having of all the fixed values, always this QB fixed, phi n fixed and QSS fixed. Therefore this Vt is fixed always. But here some variable parameter is there. This Vt sometimes this is also changed. Due to the change in the VSB, this is only the external potential which is applied at the outside the fabrication part. Therefore, if VSB changes, QB changes. If QB changes, this Vt changes. That change is defined with the help of an effect called body effect. So, what it is? QB is proportional to square root of VSB and Vt is proportional to QB. Therefore, if VSB increases, QB increases, therefore Vt increases. This effect is called as body effect, where that VSB representation is nothing but substrate bias potential, that is source to bulk potential. Already we have seen in the operation of the MoS transistor, while starting the operation of the MoS transistor, always a source has to be connected to ground and bulk is also connected to the ground. So since these two are grounded, means always at source 0, at bulk also 0. So VSB has to be Vs minus Vb, that should be equal to 0. This has to be the maintained voltage, that is VSB is equal to 0. Because of any reason, if VSB is changing other than that 0 value, since that VSB is proportional, our VSB is changing QB, QB is changing the Vt. So if VSB changes, Vt changes. That too, other than the 0, this can be in the increment value. Therefore, Vt will be in the increment value. That is called as body effect. That is increase in the threshold voltage due to increase in the substrate bias potential. Actually, once transistor is fabricated, Vt is fixed. But due to any change in the VSB, there may be a variation in the Vt. That Vt can be increased. That is called the body effect. So let's see, due to the body effect, how that threshold voltage equation can be written. By including the body effect, the threshold voltage equation is written like this. Vt is equal to Vt of 0, this is threshold voltage at VSB 0. Vt of 0 is representing as threshold voltage for the VSB 0, that is actual Vt. Plus, due to the change in the VSB, there is some factor is coming for the addition of the Vt, that is, so this total is taking as a constant, this one is taking as a constant of gamma into VSB power half. So we can write Vt is equal to Vt of 0 plus gamma into VSB power half. So due to the increase of this VSB, this gamma times of VSB, square root of VSB is added to the Vt. So Vt is increasing. This is the body effect coefficient gamma and it is representing as like this, and Vt is initial Vt plus added Vt. For example, typical value, let us take VSB is equal to 0. VSB is equal to ideal case. Then Vt is 0.2 VDD. For example, if VDD is 5 volts, then 0.2 VDD is becoming as plus 1 volt. If VSB is increased from 0 to 5, VSB is 5, then Vt is becoming as 0.3 VDD, which is greater than of 0.2 VDD. That is, if it is equal to VDD is 5 volts, it will become as 1.5 instead of 1. So, these are the typical examples for the NMOS transistor. So, like this, the Vt can be increased if VSB is a non-zero value. So, while designing the circuits, we have to be taken care always VSB is connecting to the 0, or the difference between source and bulk is always should be 0. So, source and bulk terminals have to be joined. So, in our circuits, we are going to take care that VSB connection because of this reason. That is, example, if we have taken a circuit of inverter, CMOS inverter, always this is the bulk terminal and source. So, the connection will be like this. Source and bulk has to be joined. To make VSB is equal to 0. So that there won't be the change in the Vt value. So, like this, while designing the circuits, please connect this. So, now what is the definition of the body effect? What is the meaning of the body effect? Increase in threshold voltage due to increment in the substrate bias potential. That is called the body effect. Let's see the next parameter, that is transconductance. First, what is the formula of the conductance? Generally, conductance is representing with G. What is the formula of the conductance? Conductance is the property of inverse of resistance. So, resistance is V by I. So, therefore, we can write as I by V. Conductance is definition of I by V, where I is current and V is voltage. Then, what is the trans? Trans is nothing but it is representing output as current as output and voltage as input. So, output current divided by input voltage will define the transconductance of MOS transistor. So, G is equal to output current by input voltage. Now, we are going to see the transconductance in MOS transistor. Therefore, it is representing as GM. Current, what is the current in our MOS transistor? That is represented as IDS. And what is the input voltage? Basically, we have applied two voltages. One is VGS and another one is VDS. So, therefore, here we are taking input as VGS and by maintaining VDS as constant value. So, output current is equal to IDS. Input voltage is taken as VGS by maintaining the VDS is equal to constant. So, therefore, we can write as GM is equal to change in the current, output current with respect to the change in the VGS with constant VDS value. With constant VDS value. If we have taken this IDS, dou IDS by dou VGS differentiation, we will get the value of GM. And already in the previous lecture, we have seen IDS has 3 values. IDS in cutoff, in non-SAT and SAT. Anyway, in cutoff it is 0, not required. So, we have to take IDS non-SAT equation and IDS saturation equation. So, both means we are going to have 2 GM equations. First, let us see in the IDS non-SAT and then in the IDS SAT with respect to those the derivations. IDS non-SAT equation, take it and derive it with respect to VGS, and take the IDS SAT and derive with respect to VGS. Let us see what are those values. So, what is the definition? Dou IDS by dou VGS at constant VDS. Taking the IDS non-SAT. IDS non-SAT is beta into VGS minus VTN minus VDS by 2 into VDS. This is the non-SAT equation. And derive this equation with respect to VGS. If we have taken with respect to VGS, it is equal to beta into VDS. It will become as mu n COX by WL into VDS, that is equal to beta into VDS. And now, if I take saturation equation of current beta into this, with respect to, if I derive this with respect to VGS, this is becoming as simply beta into VGS minus VTN only. So, this is in the saturation region, this is in the non-saturation region. GM in saturation region and GM in non-saturation region. Okay. So, GM is equal to this, beta into VDS, beta into VGS minus VTN, where beta is equal to, we know that K into WL or mu n into COX into WL. So, GM transconductance depending upon what factor? Just simply other than constants, VDS, the applied potentials. GM depending upon the applied potentials. From the GM, what can we define? The speed of the transistor we can define. That is, GM is equal to what? We said 1 by R, inverse of the R. If GM is equal to more means what? R is equal to less. If R is equal to less, what happened to the tau? Tau is equal to less, because tau is equal to RC time delay. That means, for getting of the faster devices, GM should be high. For getting of the faster devices, GM should be high. To get GM high, what have to be increased? VDS has to be increased. Means, to get the more speed in the operation part, we have to apply the higher value of the VDS. So, this is GM equation. Next, output conductance. Already we have seen the definition of conductance, that is 1 by R, that is equal to I by V. Now here output conductance is nothing but output current by output voltage itself. Output current by output voltage. So what are the output currents and voltages here? Output current is IDS, output voltage is VDS. So we have other voltage as constant, at VGS constant. Now let us take IDS non-SAT and IDS SAT and differentiate with respect to VDS and find the output conductance value. Let's see that. So output conductance definition is this: GD is equal to dou IDS by dou VDS at constant VGS. Taking the IDS non-SAT equation, this is non-saturation current equation, and differentiating this with respect to dou VDS will give the GD. So after differentiating, GD is equal to, this is the equation, and for using this GD or for calculating of resistance, output resistance of that device, this GD will be used. So that is R on, to find the on resistance or R channel resistance, this GD is used, that is equal to 1 by GD. So that is 1 by GD, if it is reversed, L by this total factor. So from this what can we understood? That is resistance of the MoS transistor or resistance of the channel is directly proportional to L and inversely proportional to W and VGS values. That means if you want to increase or decrease, if I want to decrease R, then what I have to change? L has to be decreased or W has to be increased. This is the option. To reduce the R, L has to be decreased or W has to be increased. For getting of that, GD will be used. This is in the non-saturation region. What about GD in the saturation region? So, the derivation with respect to VDS. But the current equation in the saturation region is what? Beta into VGS minus VT whole square by 2. There is no VDS term in this entire IDS equation of the sat. So, therefore, in the saturation region, GD derivation with respect to this with VDS is equal to 0. GD is equal to 0 means what is the meaning? Output conductance is 0 means resistance is equal to what? R on. If I want to tell R on is equal to 1 by this is equal to infinity. Infinity means what about the current? Current is equal to 0. 0 means here this GD is a change. Change it is representing. So change is infinity here. That means I is change is 0. In I change is 0. In I change is 0 means what? I is equal to simply constant. So in saturation region, the current is constant. That can also be defined with respect to this GD value. If I find GD in the saturation region, it is equal to 0. That means change in IDS with respect to change in VDS is 0. Means even though VDS is changed, there is no change in the IDS value. It means IDS is constant. So, in the saturation region, we can define transistor is acting as a constant current source by using this GD expression also. So, this is about output conductance. Let's see the next parameter. It is figure of merit. Figure of merit is used for the indication of a frequency response. To find the frequency response of the MoS transistor, this figure of merit is used. That is equal to represented as omega naught. Omega naught is equal to Gm by Cg. So, how can we write Gm by Cg as omega naught? That is, we know definitions. Omega is equal to 1 by tau or F is equal to 1 by T simply. T is equal to what? 1 by RC. We can write 1 by R as G. So, therefore, G by C. So, we can write omega or frequency as G by C from this. Omega is 1 by T or F is 1 by T. Then T is equal to RC. 1 by R is equal to G. So, G by C is nothing but the omega. So, from that it is defined like this. Gm by C. Gm is the transconductance of MoS transistor. Cg is the gate capacitance of the MoS transistor. So, if these two are substituted, we know the formulas for Gm and Cg value. What is the Gm equation? Gm we have seen already, that is equal to beta into VGS minus VT. Substitute that Gm value. What is the Cg? Cg is equal to, we know that Cg is a parallel plate capacitance, epsilon naught, epsilon insulator, WL by D. Epsilon insulator, epsilon naught, WL by D is the Cg. Now substitute these two in this equation Gm by Cg to get the omega naught. So after substituting that, it is equal to mu by L square into VGS minus VT, where it is equal to 1 by tau St. Because tau St formula we have seen. What is that tau St? Tau St is equal to L square by mu into VDS. Where VDS is equal to here written as VGS minus VT, because we are seeing the frequency response in the saturation region. That saturation region VDS is equal to VGS minus VT. So finally, omega naught is equal to mu by L square into VGS minus VT. It is using for knowing the frequency response. Frequency response means what? It shows the switching speed. Switching speed depends on the gate voltage, that means VGS minus VT. Switching speed depending upon the gate voltage above the threshold voltage and the carrier mobility and inversely as the square of the channel length. So it depends upon carrier mobility, inverse of the channel length and gate voltage above the threshold voltage. So a fast circuit requires that GM as high as possible. Why? Because if GM is high, then W is going to be high. Switching speed is going to be high. From the definition of the GM also we have seen. If GM is high, resistance is reduced, so the delay is reduced, so speed will be increased. So to get the faster speeds, GM has to be high. So therefore, omega is going to be increased. So this is figure of merit. Now, let's have a small quiz to check our understanding. Transconductance gives the relationship between, what is the transconductance? GM. GM is giving the relation between what? What is the formula of the GM? GM is equal to output current with respect to VGS. So, dou IDS by dou VGS. And it is equal to what? Output current, and denominator is input voltage. So, change in output current with respect to input voltage. What is the option here? Giving the relationship between output current and input voltage. Then, a fast circuit requires what? Just now we have seen a fast circuit requires high GM. If GM is high, then omega naught is, if GM is high, then omega naught is high. Therefore, circuit will be fast. So, next question. The variation of the threshold voltage with the applied bulk to source voltage. Applied bulk to source voltage is typically observed by plotting the dash function of the source to drain voltage. See, variation in the threshold voltage. So, here we are seeing the threshold voltage formula VT with the applied bulk to source, that is substrate bias potential. We have seen already VSB is observed by plotting the dash function of the source to drain voltage. So, what is the function here? So, VT is, we have seen, is directly proportional to QB, where QB is directly proportional to square root of VSB. So, VT is nothing but square root of VSB. So, drain current, square root of the drain current, then square of the drain current and natural logarithm. So, here our option is square root. Then, the dash of a MOSFET is affected by the voltage which is applied to the back contact. So, this is also related to the threshold voltage. The dash of a MOSFET is affected by, what is the parameter which is affecting? By the back contact. Back contact is nothing but bulk contact. Because of that, what is affecting? Simply threshold voltage is affecting. Take these are as assignment questions, that is explain the body effect, because this is very important. This is the second order effect which is existing in the transistor. So, just explain that and derive the threshold voltage. We have seen direct formula. So, derive R1 of MOSFET. Follow the textbooks of Bucknell and Neil Weste to understand these concepts. What we have seen till now? We have seen 4 parameters of the transistor like threshold voltage, transconductance, output conductance and figure of merit. I hope you understood the parameters of the MOS transistor. We will see the circuit design in the next lecture. Thank you.